Here we have a linear inequality in two variables, meaning that we need to graph the solution set and then shade the region that represents the solution to this, this linear inequality. There are a few ways to do this. I will show you one of them. The way I like to approach these is to get this into y equals mx plus b form, also known as slope-intercept form. Once you have it in that form, okay, once it's in this form, greater than or equal to, or greater than means shade up, and less than or equal to or less than means shade down. Okay, otherwise you get to use test points to test the regions, and that's a really interesting technique. It just, to me, always seems like extra work using all this test points when you can just shade up or down based on the inequality. Let's get this inequality into y equals mx plus b form, which means we basically need to think of this as solving for y, and we'll treat this inequality like an equal sign. Okay, so I subtract x from both sides, and that gives us y greater than or equal to negative x minus 2. Okay, so when we go to graph this initially, just treat this like a line, right? So what I'm thinking of is the line y equals negative x minus 2. Now, for this line, we have our negative 2 here. This is the y-intercept. Remember, this is y equals mx plus b form. This last number here is the y-intercept. And then we have a negative, just a negative here, which is really a 1, negative 1. So negative 1 over 1 is the slope. And anytime you have a slope of 1 or negative 1, your line is a perfect diagonal. Okay, so I have a y-intercept here of 2, of negative 2. So there's our y-intercept. And then the slope is negative 1 down. Okay, so we can go down 1 to the right 1, and that'll make our perfect diagonal. What I like to do when I know it's a perfect diagonal, here I have a y-intercept of negative 2. I have the negative, so I know it's going down and to the right. I just like to go to my other axis over here. So if we have negative 2 on the x-axis, that's going to give us our perfect diagonal that goes through negative 2 on the y and negative 2 on the x. Okay, connect those up. There's our line. Okay, now for shading, right? We have a greater than or equal to, and greater than or equal to means shade up. So not only do we have our line is part of the solution, but we also have to shade this whole region. Okay, there we go. So any point that lies in this shaded region is part of the solution set, right? So maybe 3, 0, right? We could plug it in and test it. Is 3, 0 part of our solution set? Well, I plug in 3 for x, 0 for y. 3 is indeed greater than negative 2, so that would be in there, right? So the shaded region represents all the points, all the ordered pairs for which this inequality holds true. Now, a very similar problem to the one we just worked is this, x plus y greater than negative 2. Notice the difference. Before we had greater than or equal to, now we just have greater than. When we did these in one dimension, just on the number line, remember we would have a hard bracket or a closed circle, and then we would move that to an open bracket or a parentheses and an open circle like this. Now that we have a line instead of a dot, the way we represent greater than but not equal to is to do a dashed line. So there's our new grid, and the new example, the line would be exactly the same. We graph the line as if it were just an equal sign. The only difference is now this line, instead of being solid, is dashed like so. And anytime you have the inequality without the equal sign, it's always going to be a dashed line, and then our shading works the same. Right? Shaded region. Some people like to shade this in very densely, like with a pencil, and really come in and get it. Some people like to just do a minimal, just a couple of arrows to show. Some people like to use colors. It's up to you how you go about shading that.